Okay, so before we get started, just a few reminders. So first of all, don't forget that the homework 3 has already been posted and it's only covered the section 1.5 and it's due this Thursday. And also the grader has already finished grading the homework 2 and then it has been returned. So I hope everyone by now already know where to check your homework. So basically you go to the My Grades menu, then I mean, this should be like all the submission history plus like if you click it, then you will see that what's the comments that the grader left there. So actually, we're very lucky that our grader is very detailedly. So I believe I glimpsed through most of the thing that he graded. So he's very thorough and he actually gives very detailed feedback. And if you want to know explicitly, like, so I essentially what I did is I asked the grader to grade like a few problems, for example. And so if you want to know explicitly like how many points count for each problem, I also announced it. So basically, if you go to where I post the homework solution, you will see that not only I upload a handwritten solution there, you will also see that what's the points for each problem that I asked the grader to grade. So you will see that you can compare with the comments there. And I also want to emphasize that please make sure that you work through all the problems because there's a 5 points devoted for the completion, for example. So if you miss a lot of problems, then you're going to not only miss the, like, for example, if you miss the problem that happens to be graded, then you already have like a couple points off. And then on top of that, if you also miss like more problems, then you will be deducted more like points from the completion. So you want to make sure that you submit most of them. Okay, all of them, I would say. And so please check the homework to return and homework 1 so you can know where you make the mistakes. On top of that, you should also go through the problems that the grader didn't grade. Those are all like equally important, right? Because I only asked the grader to grade maybe half of it. So the other half, if you don't know how to do those half of the problem, then you should also check with my solution, compare your answer with my solution. That's the whole point. I post a solution there. Okay, so another thing I want to emphasize is that I noticed that more and more people are skipping the class. I know roughly like who were here, who were not, because I have a complete record on the Zoom. So I would know who actually was not in the class. So of course I'm like, I know like sometimes like emergency might happen, that for example, the internet connection is bad, or like you have certain things that you need to, I mean, like pop out sick, you need to take care of. But the moral is that like, even though this is an online course, my recording and the lecture is for, in general, for review purpose. It's not for students to skip the class. And as I mentioned at the first class beginning of the semester, that from my past experience, especially in the fall, that students who actually skip a lot of classes turns out to have worse performance in the class, because right now it seems like the material is slightly easier, but as time goes by, you will see that the materials, once the material gets harder, then you will need to spend a lot of time just to watch the video, and no one would be able to answer the question on site. Or so I would say it saves more time if you just directly come to the class and then with my explanation, right? So then if you have question, you can right away ask the question on site, right? Rather than having to watch the video later on. And in my past experience, a lot of students will just wait and wait until weekend, for example, and then they have so many things they need to do. So they tend to postpone watching the video, and then you will just gradually fall behind the schedule. That's what I understand. And that's why I don't encourage you to skip the class, especially if you can make it, then you should definitely try to make it to the class and attend the class. So that's the first remark. Second, I want to make a quick address about this particular problem that I show you here. So this is one of the, I think, last problem on the homework 2. So this is number 21 in section 1.4. And I noticed there's another similar type of problem as well, but I just picked this one. So when you get the homework back, you might see that the grader actually take maybe 1 or 2 points off for this problem. And then especially if you use the formula for finding the inverse of the matrix. So a lot of people actually say, okay, if I have a general like general 2x2 matrix, and they directly, some students just directly use the shortcut formula to tell me that, oh, they essentially use this formula where the inverse of a 2x2 matrix is something like this. There's a shortcut formula indeed. But the problem is, how do you know, before we even cover it, how do you know this is the correct formula? So if you want to use this formula, you should justify it, right? Like, how do you know this is the correct one? You cannot say, oh, because I saw the formula somewhere, right? What I train people is to know why this formula is correct, or actually why this formula will give you the correct inverse, right? I don't want to train people who only knows how to plug in some random formula, right? So if you directly use this formula to say that, oh, the inverse of this matrix R is the transpose, then you will be taken at least 1 point off, right? So the correct way of doing this, especially before we know how to explicitly finding the inverse, you should just go with the definition of inverse. What's an inverse, right? If an inverse matrix is the matrix where after you do the multiplication, it will give you the identity, right? So first in this case, so you should not directly seek for the shortcut formula, right? Before, if you justify this is the correct formula, that's fine, right? But how do you justify this would be the correct formula for inverse? There's several ways, right? The most straightforward way actually is the same thing as how you do this problem, is that you just check whether the candidate satisfy that the multiplication equals 1. So for example, they claim, say, show that R, this matrix R, is non-singular. And on top of that, show me that the inverse is the transpose of the R. So you first find out what's transpose, right? So transpose is really just flip the whole thing. And then you really just do the multiplication, right? You take R times the transpose, right? And you should just directly check this is the identity. And you also need to check the other around. If you can show me that this 2 multiplication will give you identity, then you are done. Then that's the definition of having an inverse, right? Inverse is just another square matrix such that once you do the multiplication with the original matrix, it's identity. So essentially, this problem is not hard at all because we already give you the candidate. We said that we already kind of tell you the hints that, oh, prove to me that the inverse is indeed this transpose candidate, right? If I didn't tell you any candidate, then it's actually much harder, right? Then you need to use the way we did it in the previous class in section 1.5 to explicitly solve it. But since we already give you the candidate, you can directly use the definition of having the inverse, or what's an inverse essentially, to check whether it's indeed the correct candidate. So I want to just address this, that you at this point, you should not directly just quote this formula without justifying it. Okay, so any questions so far before we start the class for today? Okay, so if any question.
I got here a little bit late. I apologize. I was running late from another class. So I actually used that in the homework, not realizing that it was it's in the next chapter. In fact, I think it was, I used it in the last homework too. But anyway, so what you're saying is that we shouldn't be using this technique right now?
Yes, exactly. Because the whole point is that how do you know this formula is correct, right? Like you cannot just, the way I want to train student is that I want student to be able to justify each step, right? If you use this formula that we haven't covered in class, then you need to convince me that this is the correct formula for the inverse of a 2x2 matrix, right? Because otherwise, like you cannot, actually that's a good point, that when you write a homework problem, right? When you present your solution, you should pretend that you're not present your solution to someone who already know the answer. You are present a solution to convince other people who may not have the background, right? So you want to logically justify that why whatever the transpose is the inverse, right? So if you want to seek out the formula, after we prove rigorously will show that this is the correct inverse, then fine, you can use it. But before we do that, then if you use this formula, how would I know that this is actually the correct formula, right? How do you even prove this is the correct formula, right? Imagine if you want to explain this to someone who doesn't know linear algebra, who only knows the definition of inverse is a matrix B such that A times B equals identity or equals B times A, right? So that's why at this point I try to that, but of course, mathematically, this is not wrong in the sense that, yeah, this formula is correct because we already knew after, I mean, people have already proved it that this, like somewhere else, that this is correct. So mathematically, it's not 100% incorrect, but logically, it's not the right move to do it at this point. That's why I only asked the grader to take 1 point off if some people just directly use this formula without justifying. And actually, I noticed that this is actually also, this formula also appeared in problem 12 in the same section. But actually, how do you check this formula is correct, right? So you can actually, even in this case, they didn't say what's determinant A, because we even talk about it at determinant A. I believe they put something like this, right?
Yeah.
Yeah.
That looks about
so
right.
How do you know this formula is correct? You can actually check it. If someone check it, say, hey, this is the correct inverse formula, then use it, then that's fine. So for example, you can really take A, right? And multiply with this candidate, right? The formula they give you, right? And then multiply this, right? If you multiply this, if you get your identity and you also check the other way around, give you identity. If you check that, oh, this is actually the correct formula for inverse, then I'm fine you using it. Because what I'm afraid is that people only know to plug in formula, but doesn't know what does that even mean to have an inverse. What does that even mean to be having an inverse? What's the definition of an inverse? The definition is simply that if you have another matrix and you multiply with the original one, and then it's equal to identity, then that's the inverse.
So one of the things that I actually did was I went ahead and used this formula because I knew it. And then right below it, after I found the inverse, I proved it, meaning that I multiplied it by the original matrix and produced the identity. But I'm guessing from what you're saying, that would be okay.
Yeah, I think so. So the things I did tell the grader that if someone use this formula, but at the end still justify, for example, check that either the formula is correct or indeed checking R times R transpose is identity, then that's fine. Then I know you actually know what does that mean to have an inverse, right? You probably do like different things in different order. But what I want to show is people really know what's the definition of an inverse, especially at this point, because I don't want the inverse to become just a formula. And especially this formula has its own restriction, because this formula, yes, you can see only works for 2x2 matrix. What if I give you a 3x3 and say, show me this is a like inverse, what are you going to do, right? That's why it's not as general. It's not actually that general. That's why I'm very, I mean, of course, later on, once we're in like more advanced situation, we can do this after I prove it. We are going to prove it at some point that this is the correct formula. But at this point, I hope that everything should go back to the definition. Yeah.
Okay.
Yeah.
Thank you.
So, okay, I have a several questions. Can you present an example of basically one that looks like the inverse? So actually a good question. So someone just asked me that, is it possible to have A times B equals identity, but B times A is not? If both A and B are square matrix, actually it's more advanced. We didn't prove it. That's why I don't want to use it. Actually, you can show that if this is the case, B times A will automatically be identity as well. You can actually prove it. I remember they included in one of the problem as a homework exercise, but it's more involved. That's why I don't want to use it now, like, because I don't want to use something that I haven't justified. But technically, if you have one of them, and then it's n by n, the other should be true. If I remember correctly, that's one of the problem that in the textbook. But since we haven't justified it, so I don't want to just directly throw it in. And the original is, and then it's something that you need to prove. It's not easy. You need to actually justify it. So I want to go back. When I talk about inverse, I rather just stick with the definition that you need to check both directions. yeah, so that's another good point that I think the grader may take few points off. I don't think it's much, but like if you only check one direction. Yeah.
Okay, I was asking that question because I wondered if, like, when you involve complex numbers or something of that nature, if you could get in a situation where a times b works, but b times a doesn't work, or
yeah,
something of that
right
nature.
now I don't have a good example come out in head. I just remember that there's a theorem says that a property says that I'm pretty sure for n by n, and then if it's a real number case, then one of them will imply the other. But you get a good point that sometimes that there's some weird situation may happen. That's why I'm not sure whether the weird situation will happen when it's complex number. I need to actually come out see whether when I prove this extra property, does it involve using the fact that it's actually a real number or it's not, right? I doubt that whether complex would be incorrect, because if real is correct, complex should be correct as well. I have this feeling that it shouldn't matter. Yeah, but I need to double check. I don't want to tell you right away because I don't remember on top of my head whether complex will be wrong or not. I need to make sure that I don't want to tell you the wrong math fact. So let me check this, and then I will get back to you. That is there any restriction on this? Is that okay?
Yeah, that's fine. I just wondered because I work with phasors and things a lot with certain stuff, and so I was like, well, would that affect it? Like, would it come back to bite you and it only worked one way? So it was just a question that had been in my head.
That's another thing, right? Like sometimes that, like, if you're not sure, then just using the original definition is the best way, right? You just check both ways, then you have a peace of mind, right? That's why a lot of time, if you're not sure about a certain property, right? Like, for example, even this 2x2 inverse formula, I've seen a lot of people trying to use it, but memorize the wrong formula, and then they got the wrong thing. And then they didn't even realize that they got the wrong thing because they didn't go check. That's one of the reasons that I always, at this point, especially early stage, I want to stick with the original definition rather than quoting something fancy. Of course, there are so many nice fancy formula. Same for other subject, like for example, differential equation as well, right? I mean, you might, like, they even write like a dictionary type of book telling you what's the formula for all the type of solution for different type of differential equations. But do you really want to use it and just directly use it without understanding why, right? So that's the thing. I'm training like a logic here, not just knowing the answer. Yeah, knowing the answer is not hard. I mean, nowadays, like, there are so many like knowledge out there, you can easily Google it, right? But what I want to student to know actually out of this class is why this is correct, not just what is correct, and also why this is correct. Yeah. Okay, so another question. So if you want to see the graded homework, go to the my grades, right? If you go to the menu for my grades, then you should already have the submission history, and you should be able to click on the homework. You should be able to click it and then go inside. Then you will see that you might need to drop down certain things, but you should be able to, once you click inside the original homework you submit, you should see the feedback, and then also the grader actually makes some marks or circle on your own original PDF file as well. So you can see, let me know if you can't. I believe that you just go to my grade and you will see the homework submission. Okay, so good question. Good. Okay, so for today, what I'm going to do is, because I feel like that the last example in 1.5 was a little bit rushed. So I want to do one more to refresh the memory, especially for people who actually missed last week's class. So this is one of the important example at the very end of section 1.5. So in the end of last Thursday, we actually talked about we want to be able to rewrite A in terms of multiplication of L times U, right? And L stands for lower unit lower triangular matrix, and U stands for strictly upper triangular matrix. And you want to essentially the goal is actually to write A in terms of L times U. So this is another thing people want to be careful that when you do the homework 3, I will also ask the grader to pay attention to this. is that after you solve what L and U is, you should tell me what's your conclusion. Your conclusion, the whole point of doing L and U is not just to find L and U, but the more important thing is that once you find L and U, then you actually should convince yourself and write down the conclusion that A is actually L times U in this order, right? So later on, either in the homework or in the exam, I will be very picky about this. If you just give me L is equal something, U equals something, but in the whole process, I never see A equals L times U, then I will take some points off. I will also ask the grader to take points off, because the whole point is not just to identify what L and U is. You need to tell me what they're used for, right? They're used for to decompose A, right? So you need to really give me the conclusion that A equals L times U, and what's L and what's U, for example. So that's one thing you want to be careful when it comes to the homework and later on. So how to do this problem, like what we did last time. So for this thing to work, right, for your L to be in the correct format, you want to make sure that you only do type 3. So what does L and U tell us about matrix? The good thing is that L and U, because they're both upper or lower triangular. So one quick advantage is that, first of all, then you can right away calculate the determinant. Later on, we're going to learn determinant. Yeah, you can right away see the determinant of A, because both L and U are triangular. And for triangular matrix, the determinant of the matrix, it's actually very easy. It's just the product of all the diagonal. So right away, you can do you can know what's the feature of A without going through a nasty calculation. Of course, there are also definitely more application. I believe that the textbook also mentioned some of them, but I want to don't go on too far on this, because you might need to do a lot of extra knowledge on having application. But definitely one direct application that's have the most direct impact on our class essentially is that you can easily calculate determinant of A, because later on we are going to learn the determinant is actually something going to tell you whether your matrix is invertible or not right away. And the determinant of A is going to be determinant of L and U. And you can see that to calculate determinant of A, it actually takes some time. But for L and U, because they're triangular, it's much easier. And you can right away get it in 10 seconds or 5 seconds. You can directly eyeball the solution. Okay, so I want to erase this because we actually haven't talked about determinant yet, so I don't want to confuse people. Okay, so the note here is to remind everyone that we want to use only type 3. So we are only allowed to use type 3 and operations. And I want to add a remark is that not only just type 3, you also want to do top to bottom, in the sense that if you want to add a multiple of one row to another, you want to do from upper row to bottom row, not the other round, because you want to keep L to be lower triangular matrix. Okay, but the whole process, once you stick with the rule that you only use type 3 operation, right? Type 3 means you can only add a multiple of one row to another. You cannot swap 2 rows, or you cannot just multiply one row by some numbers. Those are type 1 and type 2. But other than this, the process is going to be the same as the usual when we're trying to solve a Gaussian elimination. So the techniques in some sense is old, right? You already know how to turn a matrix into, for example, REF, right? So the process is more or less similar. So let's start with this matrix. So once you start this matrix, you can see that a lot of people see that, oh, the first number, the pivot here is 4. So a lot of people were trying to swap with the second row, or trying to do some type 1 or type 2 operation. You need to avoid doing that. So what you should do is really just do type 3, right, from top to bottom. So I'm going to take out this 4 and then try to eliminate -2 directly. So I'm going to take row 1 times 1/2 and add it to row 2, right? So basically, this is what we're going to do. So I want to stick with just type 3. And of course, I mean, if you do that, then you might create some fractional number, but it should not be too bad. So once you do that, as I mentioned last time, you want to keep track of the action you just did. So I want to write a corresponding elementary matrix to represent the action I just did. So how do you get the elementary matrix? You start from the identity, right? But you want to do this particular action I just did to the identity matrix. So you want to multiply 1/2 and add it to row 2. So you can see that this would be your first elementary matrix. Okay. And you just keep doing what you did, right? So your goal is to turn it into upper triangular. So the process is the same. So I still use this pivot 4. I want to eliminate this -6. So I'm going to take row 1 times 3/2 and add it to row 3. Right? So then, okay, this would be 0 minus 3/2 and 1 here. Okay, and after the second operation, I also keep track of what I just did. So I want to add the first row, I want to multiply first row by 3/2 and add it to row 3. And as you can see, each elementary matrix only represent one action. So what I saw before, like sometimes that people might actually confuse and combine 2 actions into one matrix, and you might create some mistake here. So the best way to do this is do it one by one, so you don't mess up things. Okay, so the last thing, we're almost done. So we just need this second pivot 3/2 here, and I want to clear out this -3/2. So the last action I need to do is to take row 2 and add it to row 3. All right, so this would be S2 and keep second row and 0, 0 and 2. And as you can see, after 3 like action, right? So this is already strictly upper triangular, right? And you can see that strictly, let me remind you, strictly means that the diagonal are all non-zero. Okay, so this is our U already. Okay, and as I said, I still need to keep track of the last action. So the last action I did is add the second row to third row. Okay, so now up to here, then now the only thing we need is to find what L is. Okay, so L, I mean, remind you, if you already reviewed this part, that the formula for L is really just take the inverse of each elementary matrix and be careful in this order: E1 inverse times E2 inverse times E3 inverse. And let me just directly write down what E1 inverse is. So this is directly related to what we covered a little bit earlier in 1.5, is that we already know what would be the inverse for each type 3 matrix looks like. So the trick is really just directly take the negative of the action you just did, right? So in this case, E1 inverse would be, you take the negative, and E2 inverse would be take the negative of the thing I just circled, and same for E3. So let me just copy down. This would be E2 inverse and E3 inverse, right? And after you calculate the whole matrix multiplication, you will see that it should be, the L should be something like this. Okay. So now once we found L, then as I said, you need to let me know what's the conclusion, right? The conclusion, the whole point is really that once you found L and U, A is equal to L times U. Oh, so back up. Yeah. Okay. So L is so A is equal to L times U. So that's, I want to copy down again so people can see here. And U is let me copy down 1 minus 2, 0, 3/2 and 1 and 0, 0, 2. And how do you know that this is the correct L and U, right? As I said, I always emphasize on checking like your answer, right? So you want to check your answer, essentially, you just really directly multiply L and U, right? In this order and see whether it gets back to A. First, we want to check whether L and U has the correct format, right? So L is lower triangular plus its unit lower triangular, right? So you can see that this is unit means all the diagonal is 1, and this is lower triangular. And U is really upper triangular. And what you really need to check, this is essentially checking for your answer, is it really give you back to A, right? So this is A, right? So you want to make sure that it really give you A, right? If it doesn't give you A, then that means your L and U, one of them is wrong, or both, right? So this is a good way to check your answer while you have time, especially when you're doing homework. That's why when you write down the conclusion, it also gives you a way to check your solution, right? If you don't give me the conclusion, then which means that you probably don't know what L and U are for, right? So this is you need to give me the conclusion or show me the conclusion. Okay, so any questions so far for this example? So I hope that this will help everyone do the homework in section 1.5. Any questions? So someone want to see more here? So don't worry if you cannot copy down. I mean, I always post the lecture notes, and sometimes because I need to kind of move on, so I might be a little bit fast, but you can definitely compare your notes with my lecture notes. I always post it pretty much right after the class. Yeah. Okay, I will post the same notes that I did here, exactly the same thing. Okay, so now let's see. So today we are going to move on to the 2.1. So I actually kind of already say a little bit about determinant, but now we can officially like introduce what determinant is. So you can see that my title is the determinant of a square matrix, meaning it only makes sense to talk about determinant for a n by n matrix. If it's not squared, then there's no such thing called determinant. Okay. And the motivation, it actually comes from that we want to, determinant is a number associated to a matrix, okay? We want this number to be able to tell us whether this matrix is invertible or not. Or in other words, I want to know, once I see this number, I should be able to know right away whether this matrix is non-singular or not, okay? That's the whole point. And I'm going to do the case, 3 different cases in some sense. That case 1 is essentially 1 by 1 matrix, 2 by 2, 3 by 3, and then we will see what's the general situation for n by n. So 1 by 1 is actually a little bit like too easy in the sense that like 1 by 1 matrix is just a number, right? So you know that a number, just a one real number is invertible, then it's equivalent, or what we say if and only if that A is non-zero, right? Because what's the inverse here? The inverse in this case will be 1 over A, right? This is another number. So because A times 1 over A will be equal to 1, and the other way around also true, right? So of course, to have 1 over A cannot be 0. So right away, we know that we have a condition which tells us that when the matrix is invertible, it's when the number is not 0. So in this case, then we define, we say, okay, in the case when it's 1 by 1 matrix, then we define determine this number, determinant of this matrix to be the number A. And if we define this way for a 1 by 1 matrix, then this essentially tells us that, okay, we have this following statement. We say that then A is invertible if and only if, meaning equivalent to having non-zero determinant, right? So later on in case 2 and case 3, this will be our goal. We want to be able to define what determinant is for a larger matrix. And we also want that this number being non-zero should be equivalent to the fact that A is invertible, or meaning A has an inverse. Okay, so this is our goal. We want to be able to define determinant A in such a general situation that determinant A is non-zero would tell us A is invertible. Okay, so case one is kind of like easy in the sense because it's only a number. But 2 by 2 matrix, we need to do a little bit work. Okay, so for 2 by 2, you can see that, okay, now we have essentially, in some sense, 4 numbers to deal with here. And I cannot add any restriction on 2 by 2 matrix, so I need to be like just general. So you have a general 2 by 2 matrix here. And we want to see what condition would tell us that the matrix is invertible. Okay, so I'm going to use this theorem coming from 1.5. So it tells us that A having an inverse or A being invertible is equivalent to the following fact. You probably still remember that there was a theorem that has 3 equivalent statements. One of them is that if A is invertible, then it's equivalent saying A should be row equivalent to identity. What does that mean to be row equivalent? It means that you can, after you do a bunch of row operation, like the process of Gaussian elimination, you can reduce A to identity, right? So that's the goal here. So we want to see that once we want to, in order to turn A into identity, what's the necessary, the requirement condition that we need here. And unfortunately, in this case, I also need to separate this case 2 into 2 subcases. So the case A is when the first entry, this entry is non-zero, right? So then we're going to see how are we going to derive what we want. So you start with, I'm going to copy down again. You start with A, right? And I'm going to multiply, because A11 is non-zero. So I'm going to multiply row 2 by this number. So I'm going to do a little bit manipulation. Okay, then you keep the row 1 and row 2, you're going to have, you multiply both by A11. Okay, then I'm going to eliminate using the pivot here because it's non-zero, right? So I'm going to cancel out this term. Okay, so in this case, I'm going to take row 1 and multiply minus A21 and then add it to row 2. Okay, so then let's go to here. So then I'm going to have A11 and A12 here, and this will be 0 because I'm canceling this one. And here you're going to see this term. Probably you already see it before. Let me erase this. So this is A11, A22 minus A21, A12. Okay, so this is minus. So after you do this action, you're going to see that, okay, now I can probably stop here. So I already know in this case, A11 is not 0, right? So at this point, I already know in order for this matrix I obtained here to be able to further reduce to identity. What's identity? Identity is 1001, right? So A11 is non-zero, so we can divide some number, divide A11 to get 1 over here. But in order to get the other one, right, essentially we hope this last thing, this subtraction, to be non-zero, right? We want this to be non-zero, otherwise there will be a problem. Right? If it's 0, then there's no way you can reduce this matrix to identity, right? There will be a problem. So this tells us that at this point, it tells me if I want A to be able to reduce to identity, meaning if I want A to be invertible, then this number should be non-zero, right? So basically the upshot is we in order for A to be row equivalent to identity, we need this number to be non-zero, right? And then in a minute, you're going to see this condition, or actually this number is the formula that we're going to need for determinant A. But I want to also convince you that this would be the same formula we are going to see for the second case when A11 is possibly 0, right? Because if you want to define a formula, you want it to work for every general case, right? You don't want to have different formula for different cases. Okay, so let's see. So I'm going to keep this formula we saw here, and I will step aside and come back later. Let me call this like equation star, right? So then let's see what happened if A11 could possibly be 0, right? Because we are talking about a general matrix. Then A would be like this, right? The first thing is 0. Okay, then in this case, in order to see more easily, I'm going to swap the row 1 and row 2. So in this case, I'm going to try to turn it into identity, right? My goal will still be the same. I want to reduce this to identity, right? So now you can see that in order for this matrix to be able to further reduce to identity, right? Then in this case, I need something spatial. I need something stronger. So in order for this matrix to be reduced to identity, I need both A21 and A12 to be non-zero, right? If one of them is 0, then we have a trouble, right? So we need both A21 to be non-zero and A12 to be non-zero, right? But these two conditions can be combined into one, right? This is the same thing as saying that I want A21 times A12 to be non-zero, right? If they're the same, right? If the product is non-zero, that means both of them cannot be 0, right? But now you can see that this condition should be the same as this one, right? This is the same as A11, A22 minus A21, A12 is non-zero. Because in our case, A11 is 0, right? So A21 times A12 non-zero is the same as the star equation being non-zero. So this is back to the star again, right? So this is because we have A11 is 0 in this case. So it turns out that it doesn't matter whether A11 is 0 or not. If we want the matrix to be able to reduce to identity, we need this star equation, right? So this basically tells us the hints that, okay, it seems like that this number, whatever that is, should be the right formula for us to define the determinant. So we define for a 2x2 matrix, we call determinant A, we define determinant A to be this formula. Essentially, you multiply. So let me give you what's the general matrix, right? If for a 2x2 like this, right, you essentially multiply the original diagonal A11, A22, and subtract the product of the off diagonal, right? So this formula for 2x2 is not hard to memorize. It's actually quite easy to remember this formula. And again, if we define determinant A to be this formula for a 2x2 matrix, then we have the following fact again. If the determinant A is not 0, then this what tells us A is invertible, meaning A can be reduced to identity, right? So this is, we know now this is the right formula that we are going to use for determinant. But you're going to see that what about 3x3, right? 2x2 already spent a little bit work trying to get the correct equation. What about 3x3, right? So before we do 3x3, I want to also introduce this notation that we're going to use throughout the whole semester. Is that to calculate, so this bracket here, it stands for matrix, right? And usually people would use bar for determinant. So for example, if you say, I want to calculate the determinant of A, then you use bar, right? So if you put bar and you put a matrix, right, then you are talking about that you're calculating the determinant. right? And this is the same as calculating the formula we just said. So be careful when you write down the homework, distinguish the bracket and the bar, because bar has like all the, as I said, all the math notation has its own meaning, right? If you confuse and misuse, then it's very confusing, right? You need to let people know, are you talking about a matrix or are you calculating its determinant, right? One of them is a matrix, the other is a number. They're two different things, right? So usually we reserve the notation, the bracket for a matrix or arithmetic matrix, and we reserve this bar like this for determinant. So do not misuse, otherwise it's very confusing, okay? So now what about 3 by 3, right? So first I want to make sure everyone knows how to calculate this. I just do a quick example, right? So if A is this matrix, 2 by 2, 1, 3, 2, 4, then the determinant of this matrix, right? I use this bar notation, will be 1 times 4 minus 2 times 3. This is essentially minus 2. As what you can see here, this is non-zero, right? So you can see that because determinant A is not 0, so A should be invertible. That's actually a pretty strong condition, right? Without even calculating the formula or use the formula or doing the usual like procedure that we learned in 1.5, just by calculating its determinant, I already know that this matrix should have an inverse. Of course, finding the explicit inverse is a different thing, right? Different topic, but at least just by knowing its determinant, we already know it has an inverse, right? I don't even need to check it, right? I don't need to know what's the candidate or check it. I already know it's invertible. That's why determinant is one of the very key signature or feature of a matrix. That's why people would want to know like how to calculate determinant. If you can know the determinant, you can decide a lot of things. Okay, well, you know a lot of information about a matrix. So for 3 by 3, you can see that I pre-write a lot of things because 3 by 3 is actually slightly harder in the sense that I'm not going to do what I did with case 1 and 2 because it's going to spend like maybe the rest of the class, right? Because as you can see, just 2 by 2, we already have 2 cases, right? For 3 by 3, there will be more, but the idea is the same. We want to define the determinant A for a 3 by 3 matrix. And the formula we are going to use is going to tell us that whether the matrix or when the matrix is row equivalent to identity. And if you really want to see the detailed proof, it's in the textbook, like the section like 2.1. So what I'm going to do is I'm going to directly tell you what's the formula for determinant A for a 3 by 3 matrix. But I'm also going to tell you there's a shortcut in some sense to memorize this formula and to help you to calculate or facilitate the computation here. So first, let's see what the original formula is. So this formula is going to be the formula for 3 by 3 determinant. And you can see it's quite long. In some sense, it seems like there's a pattern, but if you just directly memorize it from the scratch like this, it's very hard to memorize this formula, okay? So that's why usually people usually use other way to do it. There's several ways to calculate this. You might already know from some other courses, so you have some other trick you can do it. But the way I'm going to teach is more general. The method can be generalized to even like 4 by 4 or 10 by 10 matrix. Okay, so we want to essentially the idea here is that 3 by 3 like determinant formula seems ugly. So we actually want to be able to simplify it by like reduce it or simplify to a 2 by 2 submatrix, right? Because 2 by 2 is so easy that we already know how to calculate it. Okay, so we want to be able to calculate a 3 by 3 determinant using some 2 by 2 submatrix. Okay, so I need to introduce some notation here. So first of all, I'm going to define this capital M1J, okay? I call this M1J to be a 2 by 2 submatrix coming from A by deleting the first row and J's column because it's 1J, right? And we know the first index stands for row and second stands for column. So how do you get M1J? You essentially take the general A, right? The original 3 by 3 matrix. You delete you cross out the first row and the J's column. So let me give you 3 examples here, right? So you could have M11. That means, okay, if you look at the original A I circle here, you essentially cross out the first row and first column, right? Then you were left with a 2x2 matrix. So this would be A22, A23, and A32, A33. Do the same thing. Capital M12 means a 2x2 submatrix from A by deleting first row and second column, right? So you do it again. So this time I want first row and second column, right? So the remaining 4 numbers will be my submatrix. And do the same thing for M13. You got it from A by deleting first row and third column, right? And you will left with another 2x2. And you might wonder, is this type of notation, capital M, can be generalized to any row and column? You can actually. Later on, you're going to see you can define a general capital Mij, meaning you get it from A by deleting ith row and j's column. Okay, but right now I want to fix with one of the index, fix one index, so we can work it more like concrete. So it turns out that we have, once you accept that, okay, we have a whole bunch of 2x2 submetrics, then you can actually determine or find out a shortcut of calculating determinant. So the shortcut is the following. So we actually observe, so let me go a little bit backwards so you can also see the, compare the original formula for determinant A. It turns out that if you stare at this formula, then you will realize that determinant A is the same as, okay, you factor out this A11 first, right? And the things in the parentheses is actually the determinant of this 2x2 submatrix M11. And subtract A12 times the determinant of M12 and plus A13 times the determinant of this M13. And you can see that now there's a pattern. Where's the pattern? The small entries A11 were corresponding to the determinant of this capital M11. So the index match, 11 corresponding to 11. And same thing here, 12 corresponding to capital M12. But this one thing you want to be a little bit careful or notice is that there's a negative sign in the second term for A12, right? So after we work with this, in a minute, I'm going to show you that when you calculate determinant for either 3x3 or 4x4 or higher, if you want to do this type of reduction to a smaller matrix, you need to be careful. Like there's always this sign, alternating sign issue. So here you can see that there's a plus, minus, and plus if you want to like stick with this formula. And later on for 4x4, there's always like this alternating sign things going on. So I'm going to show you later on. And in other words, if you want to rewrite it, the determinant into the bar notation, you can see that this is essentially A11 times this determinant of this matrix minus A12 times this determinant of M12 and plus A13 times determinant of M13. Okay, so I'm going to stop here before we go further about the formula. So what I'm going to do now is to show you a concrete example so you can really see how to calculate a 3x3 determinant. So, okay, if this is the first time you saw this, then you definitely need to practice this, right? A lot of time, like you need time to work on. This is just algebra and you need to memorize some pattern. So first of all, let's see. So this is what we call the first formula we saw here is what we call the expansion along first row, right? Why I say that? Because you can see that the number, the entry we take it out here is A11, A12, and A13. That's all the entries in the first row. Later on, you're going to see you don't have to go through the first row. You can choose either first column or second row or second column, whichever is easier, right? Then you can do it. But for now, let's stick with the expansion along first row and we calculate the determinant. And once we are more familiar with the techniques, then we switch to more general scheme. So determinant A here, I'm going to stick with what we just did. I'm going to expand along this first row. So follow the formula above here, right? So this should equal to A11, which is 2, times the remaining determinant, right? So what you do is you take A11 and cross out anything passed through A11, right? So essentially crossing out first row and first column. So the remaining 2 by 2 determinant is this. So you have a 2 times this whole thing. Of course, I need to calculate this 2 by 2 later on. And plus minus A12. A12 is 1, right? I'm just write down everything so you can follow. And A12, you need to get the M12 determinant, right? So you cross out anything passing through A12. So that means first row and second column, right? So the remaining will be 1, 3, 4, 5. Okay. And plus A13, which is 6, times the remaining submatrix. So you take out first row and third column. So that would be 1 minus 2, 4, 2. So once you do this, then you can see that, okay, we managed to reduce a 3 by 3 matrix to something about determinant of 2 by 2. And determining 2 by 2 is so easy. We already know how to do it. So let's calculate here, right? So 2 times, okay, 2 by 2, this is minus 2 times 5, that would be minus 10. And minus 2 times 3, that's minus 6. Minus 1 times 5 minus 12, right? And plus 6 times 2 minus minus 8, right? So now let's see. So I have, that's minus 16, minus 32, and plus 7, and this is 10, and plus 60. So this is going to be 35. Okay, so again, this determinant is non-zero. So you can actually see that this matrix is going to be invertible. Okay, so this is one example of calculating 3 by 3 determinant using the expansion along the first row. And as I said, this scheme should be able to generalize to any matrix. So for example, later on, if you say you want to calculate a 4 by 4, then you can do the same thing, right? But then you would reduce to a determinant of 3 by 3, right? Then maybe you need to do further, like calculating 3 by 3. So most of the time when we do the, when we calculate the determinant by hand, let's say by hand, we do this kind of reduction, right? Because of course, you might have some general formula for 4 by 4 determinant, but it's going to be super messy, right? And then it's super long. So I'd rather do this like kind of like a shortcut. And this pattern is easy for me to memorize. Yeah, actually, we are going to do a 4 by 4. You're going to see, I'm going to do an example. Hopefully I can get to that example. It's not that bad actually, because once you get familiar with the techniques, you just need to memorize how to reduce to a smaller matrix. Okay, so, but first, of course, you need to know how to do a 3 by 3, right? Before talking about 4 by 4, no, you need to first knowing how to do a 3 by 3. Okay, so after this, I want to say essentially, I just said, right, the same idea should work for n by n. So this is when we actually generalize to more general situation. So if we want to talk about general situation, then I really need to introduce like the most general formula here. Okay, so again, we have, let's say we just have a general n by n matrix, any n, right? 10 by 10, 20 by 20. And now, because we want to use the trick of reduction, so I need to essentially introduce this Mij that I talked about. This is what we call the submatrix, right? So Mij is a n-1 times n-1 submatrix. And you already know, how do we get it? We obtain from A by deleting the row and column containing Aij. Or you essentially, you can say deleting i's row and j's column, same thing, right? And then you remember back in the 3 by 3 case, what we need is actually the determinant of this Mij, right? So this determinant of Mij is what we call the minor associated with the entry Aij. Right, remember when we calculate the formula, we need, if you take out A11, you need to multiply by a determinant of M11, right? So each minor is come with the entries Aij. Okay, then we actually want to define, I need to define this cofactor of Ai by the following. So let me put it here. So determine the cofactor of Aij by, this is the cofactor. So I'm going to use this capital Aij. This is actually the exact thing we are looking for. Mine looks a bit scary, but if you think about it, that this is exactly, not only we need the determinant of this submatrix. Remember, I just told you that there's an alternating sign issue, plus, minus, plus, right? You can see this -1 to the I plus j's power, exactly, essentially, like it's exactly for this alternating sign purpose, right? So the alternating sign actually, essentially, you already involved in this, included in this Aij. We need to incorporate this alternating sign. So for example, remember back then, if we encounter A12, there's a negative sign, right? As you can see, because A12, the index is 1 and 2, right? So 1 plus 2 is 3, right? So you will have -1 to the third, that's a minus. That's why when if you go back, right, let's go to see the A12 here. That's why you can see that in front of A12, there's a minus sign. This essentially comes from your cofactor here, the -1 to some power to the I plus j. Okay, so that's exactly why there's an alternating sign here. So once we analyze the shortcut formula, right, then we can actually see the pattern here. So we can actually define a general determinant A formula for any n by n matrix. So we say determinant A is essentially just a scalar number defined inductively, right? Because we go from 3 dimension to 4, 4 to 5. So this is what we call, or the other way around, depends on how you view it. So we define it in this way. If dimension is 1 by 1, right, n equals 1, then we already know determinant A should be just whatever the only number there. If it's higher, like dimension 2 by 2, 3 by 3, anything higher, then we have this formula we just saw. So this cofactor Aij is actually already incorporating the alternating sign that we saw. So this is a very general formula, which works for any n. Okay, that's the most general one. And as you can see, if you want to argue here, I only give you the formula that's the expansion along the first row, right? So this is the formula for expansion along first row. You can actually have a general formula, which I'm going to show you in a minute, that you can have a general formula for determinant A. And in terms of expansion along any row or column, but the pattern is the same. What's the pattern here? If you want to say do the expansion along the first row, you do small a11, right? You multiply by maybe plus or minus times determinant m11, and you plus a12 times -1 to some power, maybe plus or maybe minus, and then you take the determinant of m12, right? So then you might argue that, okay, like this is okay. I remember the A11 match with determinant M11, right? Because the index match. But how am I going to remember the alternating sign, right? We always need to go back to this -1 to the I plus j power. It turns out that I'm going to show you pretty soon that there's a pattern, like a shortcut, a trick that you can memorize the alternating sign. Okay. So first of all, before we do that, I want to show you that we actually have a general formula for so here I want to also emphasize this Aij. Let me just write down the formula here again for completion. So Aij here is just the cofactor, right? Okay. So it turns out that we can also compute determinant A using cofactor, the expansion for any row or column. So you can see that for any determinant, right, as long as it's more than 2 by 2, if you want to say expansion along ith row, right? Not necessarily one, the first row, but ith row. Then you take out A1, I1, I2, and you match with the corresponding cofactor, right? And add them up. That will give you the determinant. Or if you're not happy about the expansion along the ith row, you can do the expansion along j's column. And then you can use this, right? So A1J, A2J, right? Corresponding with the like match with the corresponding cofactor, right? But of course, when like I'm not going to trick everyone to always calculate like a very large matrix, right? I will say we're going to go at most 4 by 4, right? 5 by 5, 6 by 6 is going to take a while, right? But at least you should know how to do 3 by 3 and 4 by 4 case, right? Like that's the basic. So right now, what I'm going to do is I'm going to, where's my matrix? Okay. So I'm going to do this following example. So I'm going to use the same example as above. So I remember we just calculate one. So this 216, 1 minus 2, 3, 4, 2, 5, this 3 by 3 matrix. Here, earlier, we calculated the determinant using expansion along first row, and we got the number to be 35. I want to redo this example, but expand it along different row or column. But I can show you that you should get the same number, right? The determinant should not depend on which row or column you do the expansion, right? It's a signature associated with this matrix. It should not change, right? It doesn't matter how you calculate the determinant. So I'm going to do this. So I'm going to compute the same matrix again. So let me copy down here, 4, 2, 5. Okay, so this time I'm going to do the expansion of second row. Okay, second row. So that means I'm going to take the entries from here, right? So that means first give you what's the original formula. Okay, so if you do this, that will be A21, right? Times the cofactor. I'm just directly write down the cofactor. Right, this is the A21 with the corresponding cofactor. Plus, I'm doing second row, so it's A22 times minus 1 to the 2 plus 2 times determinant of M22. Right now, I'm trying to do everything like step by step. Once you're familiar with it, you don't need to do all the middle step. You can directly start computing, right? So, okay, so what's A21, right? First entry in the second row, that's 1. And you will see that now we do have an alternating sign as well. So you have minus 1 here, right? Because it's minus 1 to the 3. So there's a minus 1 here. And determinant of M21, right? So you take out A21 entry, you cross out any row or column passing it. So the remaining 2 by 2 is 1625. You want to do it slowly, especially if this is the first time. You want to like make sure you got the right thing. A22 is minus 2 times minus 1 to the 4th power, that's 1. Determinant M22, so circle out minus 2, cross out anything passing it. Okay, and plus A23, that's 3 here, right? But you'll have minus 1 to like to the power, so this is minus 1, right? And so this is determinant M23, circle out 3, cross out everything else. So okay, so now first, before we calculate it, I want to point out that now what's the alternating sign pattern here? You can see that in this case, it's going to be minus, plus, and minus. Okay, so back then, if we do first row, it's plus, minus, plus. If it's second row, it's minus, plus, minus. Okay, so I'm going to show you in a minute that how do we directly memorize the pattern. But first, let's finish the calculation here. So I have minus 5 minus 12 here, minus 2, 10 minus 24, minus 3, 4 minus 4, that's a 0. Yeah, so this is 0. 7 and plus 28. So that's 35, right? So same answer. So same answer as previous example. So this is the same matrix as earlier. So of course, the same answer as before, right? So you can see that that's how you compute the determinant of 3 by 3 using different expansion. So now the thing is that how do we recognize the sign, alternating sign, right? If you have to go through this cofactor every single time, it's a little bit annoying because you need to keep track of those things. So one trick I can tell you is that what I usually do is, if I want to calculate 3 by 3 determinant, how do I memorize the plus or minus, right? So you start with the very first entry, the A11, you put a plus. Any other row or column, just do the alternating sign. Right, you start with the 1, 1 entry, put a plus. Everything else is alternating sign. So you can see that this also match with what we did. The first row is, when we do the expansion of first row, is plus, minus, plus. When we do the second row just now, it becomes minus, plus, minus. And you can do same thing for a 4 by 4, right? If you have a 4 by 4, same thing. So this is 3 by 3 pattern, right? 4 by 4, again, start from 1, 1 entry, because 1, 1 will always be plus. And you do the alternating sign for the remaining, right? So you start from 1, 1, always put plus. So this tells you later on, if you calculate a 4 by 4 determinant using the reduction like this, let's say if you expand along the second column, for example, I just randomly pick 1, then you're going to see a minus, plus, minus, plus alternating sign here. That's essentially like one way I actually memorize the alternating sign. So I don't need to go back to the cofactor. I just need to take care of the determinant of the submatrix. Okay, so that's actually a trick that I find it very useful. And then I don't need to always write down -1 to some power. That's annoying, because once with this kind of chart, it's easy to just directly find a pattern. So the trick of finding determinant of A, now you see how we expand along different row or column. So there's a choice you can make, right? Which row or which column. So the moral is always, you want to expand along the row or column that contains the most zeros, right? Because you're going to take out those factors. If the certain row or column has a lot of zeros, then of course expand along that rows, right? Then there will be a lot of thing what looks like 0 times something, then you can just ignore it, right? So this 4 by 4 example I'm going to show you, probably I won't have time to finish the whole calculation. I will come back to this, but I want to write down the expansion for you so you can actually go back and then think about this. As I said, now I have a 4 by 4, quite large, right? But if I want to do the expansion, I'm going to pick the one has the most zeros. So you just eyeball it. You can see that the first column has double 0. So I'm going to expand along this one, okay? And to help me memorize the sign, alternating sign, you can go back to my chart here. You start from plus on the first 1, 1 entry. So the alternating sign, it's going to tell me it's plus, minus, plus, minus, okay? So now let's see, okay? Then I can start the expansion. So expansion along first column. So the first entry is 0, okay? I'm just going to tell you what's the corresponding 3 by 3 matrix, but technically you don't actually even need to write down because it's 0 times something. It's just for completion. So if you want to find this A11 entry, then the corresponding 3 by 3 will be 4, 5, 1, 3 minus 2, 2, and minus 1, 4, 0. Okay, so this is the first thing. Plus, minus the second term, it's 0, right? So again, I just write down the corresponding submatrix for completion. Technically, you don't really have to though, okay? Plus, minus, plus, and the third one is -1 here, times the corresponding 3 by 3, right? So 3 by 3, you can see that, okay, I cross out anything passing through this -1. So I will have 1, 2, 3, 4, 5, 1, and minus 140. Okay, and last one plus minus, and last one is 2 times this corresponding 3 by 3. Okay, so you can see that actually, like what I said, if you do it expanded along the row or column has the most 0, you don't even need to care about this 2. Even sums of row and columns are positive and odd sums. Yeah, exactly, right? So that's why you see the plus and minus alternating. And once you start with 1, 1, you know that the rest of it should be alternating sign. That's why I usually use this chart here, because then I don't need to like, I mean, of course, if it's higher dimension, then it's probably easier to do with the minus 1 to the I plus j. But with like smaller, you can actually see the chart, then it will right away like help you to memorize it. This is another trick. So I'm going to stop here. So the only thing we need to do to come back to calculate this is really to figure out the determinant of this 3 by 3. And this goes back to the previous example we did, right? So as you can see, once you know how to do this reduction pattern, then you reduce a 4 by 4 determinant to 3 by 3. But that's why I say in order to do 4 by 4, you need to know 3 by 3 first. And in order to do 3 by 3, you kind of need to know 2 by 2. So I will leave you to do this like over the next 2 days. I will come back to this example to finish up on Thursday. And for 2.1, we are almost done. I only need to tell you a couple extra feature for the determinant in general. Then we will, on Thursday, we will also move on to the 2 by 2 to discuss more about what's the property of determinant. For example, if you have a product of n by n matrix, the determinant should be determinant of A. If say you want to calculate determinant of AB, then it will be the same as determinant of A times determinant of B. Okay, so I will do a couple more in 2.1, then we will move on to 2.2. And don't forget the homework 3 is due on Thursday. And if you have any question regarding the homework 2, please let me know. Okay, so you should definitely check what's the grade and what's the mistake there. Okay, so everyone's free to go if you don't have any questions.
Have a good day.
Yeah, you too. Okay, if there's no question, then I'm going to end the meeting.